What's up, Marco? What's up, other subscribers? We're going to be looking at 3.6 second order linear equations here. We have this harmonic oscillator. It's problem 16 / problem 24. So we'll look at parts of both of those questions. Our mass, M is 1, spring constant, spring force is 8, and B is 0. Let's go ahead and get this out of the way. When B is equal to 0, we have an undamped oscillator, right? Because that's our damping force. And the equilibrium point at the origin in the phase plane is a center. All solutions are periodic, and the mass oscillates forever about its rest position. The natural period is 2 pi times square root m over k. 2 pi square root m over k. 2 pi square root 1 over 8, or pi over square root 2. This didn't jump out at you, we're about to do it anyways right here. So we can go and write this as, d squared y dt squared plus b dy dt plus ky, right? Well, there's no b, so right now we just have d squared y dt squared plus 8y. Lambda squared plus 8. Lambda is equal to plus or minus 2 square root 2 I. Square root 8, square root 4 times 2, which simplifies to 2 square root 2. Square root of 4 is 2, square root of 2, we just write a square root 2, right? So we've talked about the natural period. Natural period is important to understand later, especially when we talk about the force period. When these are equal to each other, or like very close to each other, we get the beating effect, which is like when you hear the pianos that are like out of tune. I think that's because like they can either like amplify each other or decrease each other. I'm not really quite sure on that. But yeah, another part of this question was to find a general solution for y of t and v of t, because you eventually want to get a y of t versus v of t acceleration versus velocity graph. So to do that, we would take this eigenvalue and write, and we're going to use the positive one. There's no real part. Okay, no real part. So let's go ahead and use Euler's. All right, cosine of 2 square root 2 so I goes away, right? Y of t is equal to k1 cosine of 2 square root 2t plus sine of 2 square root 2t. That was really dumb. All right, y of t and k of t. So now our v of t is negative 2 square root 2 k1 sine of 2 square root 2 t plus 2 square root 2 k2 sine of 2 square root 2 t. I'm terrible at everything I do. This is cosine of 2 square root 2t. All right. Right here you can kind of see a spoiler alert, right? Y of t 0 is 1. The initial condition is y of 0 equals 1. V of 0 equals 4. So if y of 0 equals 1, sine of 0 is 0. So we only have k1 times cosine of 0, 1. k1 times 1 is equal to 1. Or k1 equals 1, right? Let's go down here to this next one. Sine of 0 is 0. So we have 4 is equal to 2 square root 2. k2 of cosine of 0 is 1. k2 is equal to 4 over 2 square root 2. That's just why we have this right here for our y of t and v of t. Or y of t and v of t. Now earlier I mentioned that when it's undamped, when it's undamped, the origin, there's a center, and it circles around. So we know that from b is equal to 0. Also, you can just know, it's kind of the same thing, but when there's no real part, and you just memorize, when there's a positive, negative, or no real part, what it looks like. When there's no real part, it's a center, as we see here. When there's a positive real part, it'd be an unstable spiral going away from the origin. When there's a negative real part, it'd go towards the origin, a stable spiral. And then our only question really is to figure out, is this clockwise or counterclockwise, right? So yeah, that's a good little review of natural period, undamped, underdamped, overdamped. This down here at the bottom is our y of t versus v of t graph. I think this kind of makes sense. So you can see that v of t is larger, y of t is this smaller black line. The blue line is our v of t. Our phase portrait, I know this is like a circle for this one, but in this scenario, our phase portrait is more ovular, actually. It's more ovular. You could plug the equations in the Desmos and probably see that, but yeah, so this is a quick little review on harmonic oscillators, natural period. In fact, we can go ahead and make this a better video about, underdamped, undamped, overdamped, critically damped. So I'm going to write some rules here. All right, so we're going to add some of these rules right here. I accidentally ended the video, so I'm not sure if it's going to merge well. But we can go ahead and say that if b squared minus 4km is less than 0, underdamped. If it's greater than 0, then it's overdamped. It's equal to 0, it's critically. And that is when we have repeated roots. All right.